Let's see. Then. Have you done this?
Did you finish your PDD?
Yeah, I think in mine.
I did you?
I did it. Tuesday.
I have mine done, but I have anxiety. Like it's terrible.
I'm looking at last year's stuff and I'm like, I haven't written as much as they did. Am I written wrong?
Because my problem statement is like 2 sentences.
Mine is 8 sentences.
Yeah,
Yeah.
because like that's the way I kind of see it. It's like when Meryl was talking about it, it's like, yeah, it's supposed to be like the question in a word. Yeah, well, I mean,
What question?
I don't know,
You gotta read mine, just mine, I don't know.
because the way he explained it is like basically like with your problem statement document, like you wouldn't know how to actually do what you're doing, but like you should be able to identify, okay, well, like this is the problem. Research I can take it. So,
But then it says, somewhere else, it says you're not supposed to answer.
no, for the problem statement, he does say it's supposed to be like a solution independent description of the concepts.
What does that mean? Like, you could
Basically-
put it in better terms.
I asked him about it, he said months, I mean, basically, he said, this part. Just must do this.
Yeah, that's what I did too when I showed him.
Did you put number?
No, I didn't put numbers in the document.
I didn't put down on somebody.
All the numbers go in like the design, like the
Okay, okay.
objectives, constraints and functions or whatever. Like, yeah, your problem statement should basically be outlining what is wrong with your current design. That's how you're going to fix it. So like in this case, like for you, something to be like wishes to design it and we'll send you containing break and acceleration. Produce weight person.
I did put wait for loading. That's not gonna be going.
I mean, the class keeps getting smaller.
Well, it's also, that's true, it's already 5 coming. I was gonna say we have
But it gets bigger in or.
anyways. Also,
It's pretty good. I'm gonna check an email and flag it.
All right, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing?
Working on a problem statement.
Okay, all right, good. All right, so it's week 5, time for our third ANSYS activity. So after this activity, we're pretty much right back on schedule. So the last couple of activities, we kind of been doing them pretty quickly over the span of 3 weeks, but after this, we'll kind of get into a steady diet of ANSYS activity once about every 2 weeks. Okay, and this activity kind of marks the turning point too, because this is kind of the last activity where I consider to be going over the basics of ANSYS. So after this activity, I would say that I'm pretty confident that you guys are pretty familiar with how ANSYS works, in general. Okay, of course, there's still more information that we need to learn about some of the more advanced features, and we are going to cover them later in the class. But at the very least, you'll be able to take most geometries after this, and at least do a pretty good job of doing it in simulation. Okay. All right. So what is this activity about? So this activity is going to be focused on assemblies, and so we have an assembly of parts here. And so we are going to be doing a finite element analysis on a three-way signpost. Okay, so you see these on the freeway all the time. This is the signs that you see on the freeway that tell you you're about to miss your exit, and so you just swerve across 3 lanes of traffic and then piss off everyone around you. So that's what this is. Okay, so we're going to be loading this geometry into ANSYS. We're going to be doing the analysis, and yeah, we'll be going from there. All right, so this activity, the due date for this activity, you have about 10 days to do it. So the due date is going to be Monday, October 7th. Okay. Any questions I can answer before we get started for today? Okay. All right, so let's go ahead and get started. So just like before, go ahead and start up ANSYS Workbench if you haven't done so already. Okay. All right, so I've already kind of started that up. Okay. And then also what you can do while ANSYS is starting up is you can download the CAD file that you need for the activity. Okay. You can download the PDF too, that would be helpful, but at the very least you need the CAD file. And so if you go to the activity on Canvas, you'll see that there are two files there. And so one file is the solid signpost geometry base, and so that's the one we're going to be working on for the activity today. And then at the end of the PDF, there is another finite element assignment that you have to do, and that involves the second CAD file here called assembly.stick. Okay, but for now, we're just going to be working on the solid signpost geometry base. Okay, so everyone's able to open up ANSYS. Okay, cool. All right, so just like before, let's go ahead and let's load up a static structural simulation. So let's click static structural here and drag it into the project schematic space. Okay. Let's load in our geometry. So just like we did in activity 2, we're going to right click on geometry. We're going to go to import. Okay. And then you're going to browse for the file that you just downloaded. So click browse, and then you're going to click on solid signpost geometry. And it should load in pretty smoothly because this geometry was actually created within ANSYS itself. Okay, and actually in a later part of the activity, you're going to be modifying the geometry as well. Okay, so before we jump into ANSYS Mechanical, let's go ahead and add a separate material. Okay, so if you remember from activity 2, the only material that ANSYS loads by default is structural steel, right? But for this activity, so if you go back to the PDF, you'll see that we actually need 2 materials for this activity. Okay. All right. So one material is going to be structural steel. Okay. And so the post here is actually made of steel, but the actual sign part, so this kind of rectangular block up top, that's going to be made of aluminum. Okay. So we need to add aluminum alloy to our project here. Okay. So in activity 2, we went over how to add how to add a material property from scratch. So we created a new material property and we manually added its Young's modulus and Poisson's ratio. Turns out ANSYS actually has a library of materials that you can actually use. Okay, so just like in activity 2, let's go ahead and double click on engineering data here. So that's going to bring up the material selection window. Okay. Okay. And so instead of adding a new material here, what you're going to do is you're going to go to this button at the top called Engineering Data Sources. All right, so you're going to click on that button, and you're going to see all the different materials that ANSYS has available to them. Okay, so there's different categories here. So if you go to the kind of top window here, there's different categories of materials that you can use. Okay. Interestingly enough, there's also kind of fluids that you can add in, and thermal materials, magnetic materials. Because ANSYS actually has the ability to do heat transfer and fluid mechanics simulations as well. Okay. But for our purposes, we just want to do general materials. You're going to click on the for me, it's row 4 with general materials. Okay. And so what that's going to do is that's going to change the change the menu here in the middle. And you're going to see all the different kind of general materials that are available to you. And so you can see we have some materials here like gray cast iron, we have magnesium, polyethylene, stainless steel. Okay. So the one that we actually want is aluminum alloy, which is near the top. Okay. So if you click on aluminum alloy, you can see its materials here at the bottom. So it has a Young's modulus of about 7.1 times 10 to the 10 times 10 to the 10 pascals. Has a Poisson's ratio of 0.33, okay? And all the other properties are added in as well, okay? Most notably, you're going to see that the density is also added into this material as well. Okay, so to add one of these kind of, these kind of built-in materials to your project, what you're going to do is you're going to click on this plus arrow next to that material. Okay. Oops. Okay, so after you click on this plus arrow, you're going to see that there's going to be a little book that kind of gets added next to that material. Okay, And so if that book appears next to aluminum alloy, that means you've added the material just fine. Okay. And so if you go back, if we go back to the previous menu, so to go back to the previous menu, you're just going to click on engineering data sources again at the top. What you're going to see is that you should have two materials added to your project now. So you have a structural steel. So structural steel was the original material that was there before. And then we also should have aluminum alloy as well. Okay. And you can kind of click between the two and you kind of see the difference in their properties. So you can see that structural steel is much stronger. So it has a Young's modulus that is maybe about 4 times as much as aluminum alloy. Okay. And it's a lot more dense. And so if you check the density, it's 7,850 kilograms per meter cubed. Okay. Whereas aluminum alloy has a density of 2,770 kilograms per meters cubed. Okay, so steel is roughly about 3 times as dense or 3 times as heavy as aluminum alloy. All right, any questions on this? Everyone able to add aluminum alloy? Yes.
How did you get the aluminum alloy again?
Sure. So from this engineering data kind of menu here, you're going to click on this button, engineering data sources, and so that's the button with all these 3 books next to it. Then that's going to open up some new menus here. So this kind of reveals all the different kind of built-in materials that are in ANSYS. And so you're going to click on General Materials. And under General Materials, you're going to see an entry for aluminum alloy, and then you're going to click on the plus sign next to it. All right. Any other questions on this part here? All right, so we are done with material properties. And so after you've added the material properties, go ahead and double click on model here. And so what that's going to do is that's going to open up ANSYS Mechanical, and that's where we're going to spend the rest of the activities.
Just to ask, Professor, what was the keybind to reset to original settings?
It should be, I think, Control R, but I usually just do it from the menu. And so, are you want to reset from the workbench?
No, just because I had an issue with the homework where I accidentally deleted my project and I didn't want to go back to the home screen.
Oh, I see. Yeah, I think it's Control R for reset.
Control R for reset. Thank you.
Yep. Okay. So once you open up ANSYS Mechanical, you should see your geometry load in. Okay. So you can see here we have kind of 2 distinct parts here. We have the aluminum sign and the steel post. All right. So first thing we're going to do, if you remember in activity 2, remember when we added our aluminum material property, we needed to assign that material to certain parts of our geometry. Okay. And so back in activity 2, it may have seemed kind of a little bit tedious to kind of do that. We kind of spent all that effort to kind of add in the material and then we have to assign it. Okay. The reason ANSYS does that is because if you have a multi-part assembly like this, you can actually assign different material properties to different parts of the assembly. Okay. And so if you go to the left-hand side of the screen, you can see here that we have a list of the geometries here. You can see here that we have 3 parts, and so we have 1 part for the sign itself. Okay, and if you click on the sign, you're gonna see it highlight in the window over there. We have 1 part for the post. Okay, and then we have a 3rd surface there called WX2 application surface. I'll explain what that is in a second. But first thing we're going to do here is we're going to assign the materials for the sign and the post. Okay. Okay, so if you recall from activity 2, the way to assign a material property is that you need to click on the part from the geometry submenu. Okay. And then you're going to go to the bottom left-hand side of the screen where you're going to assign the material. Okay. Okay, and so if you look at the bottom left-hand side of the screen, right now the sign is assigned a material of structural steel. Okay. But for this activity, we're going to assign the sign itself to be aluminum. So we're going to change this. And so with the sign selected here, you're going to click on material assignment, and then you're going to click on aluminum alloy, okay, to switch that material. Yes, question.
Is there a difference in what ANSYS does if you switch the material in that menu versus making a material assignment in materials?
Wait, a material assignment where again?
On your materials, like. If I like right click the materials folder, right?
It should be the same, and so if you do either one, it should give you the same.
Oh,
Yeah, typically I do it under geometry just because I know this one opens up the menu, so it's a little bit hard to visualize the part. But it should be fine to do. Question, yes.
What if the material isn't popping up when you click on so you click on that one and
Yeah.
it doesn't show, it shows those top three with the star, but doesn't show those aluminum alloy or structural steel.
Yeah, so you probably need to go back into Workbench, so I would close mechanical. And then just make sure that when you're back in mechanical, or excuse me, when you're back in Workbench, you click on engineering data. And just make sure that the two are here.
Yeah, they're there.
Are they there? And they're not showing up on the, I'll come by in a second. All right, any other questions on this part here? Okay. All right, so for the post, we actually don't need to change anything because the post is made of steel, so we're just gonna keep it at the default, okay? Okay, so let's talk about this WX2 application surface, okay? Okay, so if you don't know where this is, you can rotate the model around, right? And you can see that this WX2 application surface is kind of almost like a very thin, it almost looks like a piece of tape that's kind of going from the bottom of the signpost up to the top. Okay. And so if you go back to the specifications, right, you'll see that one of the forces that we're going to be applying on the signpost is a wind pressure force. Okay. And it's going to be applied all on the left-hand side of the post and the sign. Okay. In fact, it's going to be a spatially varying force too, which we're going to account for, as well once we assign the boundary conditions. Okay. But because this force here, this force here is being applied on two different parts at the same time, right? And so we need to apply it both on the post and on the sign itself. We need to create a separate surface here in order to, be able to apply that force. Okay. So that's what this kind of strip is. And so this strip here, it's not going to add anything structural to the model itself. It's not going to add any structural strength. It's really almost kind of just like a phantom surface or a ghost surface that we're going to use just for the sake of applying boundary conditions. Okay. So this technique of kind of adding additional surfaces to your model to make it easier to assign boundary conditions is very common in ANSYS, because a lot of times you're going to have situations where you want to apply a boundary condition, but ANSYS doesn't automatically create a surface that makes it convenient to do so. Okay. So for instance, this wind force is a perfect example, because we know the wind force is going to strike. The wind is going to strike the signpost from the left. Okay. And so it makes sense that the wind force is only going to be acting on the left-hand side of the post. Okay. But if you try to select that part, so let's assume that this application surface isn't there, right? And so the only surface that you can click on for the post applies something on the entire post itself, right? And so that necessarily wouldn't be accurate, because you don't want to apply the force around the entire circumference of the post. You only want to apply it on just one side. Okay. And so we've created this additional surface right here to basically allow you to apply force in that direction. Okay. Okay. But because it's kind of a ghost surface right here, it's it's not like a real surface, right? And so we have to specify its thickness. So ANSYS is basically assuming that you do have a very thin strip of material that goes up and down, right? And so just for kind of completeness sake, just for ANSYS' sake, you need to assign a thickness to this, okay? And so if you left click on WX2 application surface, you should see in the bottom left-hand side of the screen that there is an entry for thickness down here, right? And it's highlighted in yellow. And so that thickness is basically going to define how thick that strip actually is. But because this surface here, we don't actually want it to contribute to the structural strength of the material itself, we're going to assign a very thin thickness here. We're going to assign a thickness of 1 e to the -3 inches. Okay. So basically 1/1000th of an inch. Okay. So basically, it's just not even going to be there at all. And then for the material, you can just keep it structural steel. It's so thin that it's not, it's not going to contribute. Okay. Any questions on this? Okay, I know a couple people are having a, so let me go ahead and move on to the next part. There's a bit more that I want to talk about with the assemblies, but we'll talk about it after the meshing. Okay, so for those of you who are kind of already ahead, go ahead and start working on the meshing. Okay, so I want you to mesh this this geometry here. Okay, but we're going to take advantage of the fact that we have an assembly of different parts, and so I want you guys to apply a different meshing methodology for the sign and a different meshing methodology for the post here. Okay, and so I want you to create 4 different objects in total. So I want you to create a sizing object. And so that sizing the first sizing object is going to specify the sizing for the elements of the post. Okay. I want you to create a method object. Okay. So the method object is going to specify the border and the shape of the elements for the post. And I want you to do the same things for the sign itself. Okay. So in total, you should have 4 different objects under meshing here. So 2 sizing objects and 2 method objects. So go ahead and specify that for the model, okay? And let me for those of you who can work on that, and then I'm going to come around and kind of help the people that are struggling with it here. Okay. Sure.
I closed this one and I opened it back up. I went through.
Yes, it's interesting that it comes in when it had no material assigned to it at all. Usually for structural simulation, it should assign structural steel like. It's really strange.
They haven't even known the solid. It's around the settings so that you can see.
Yeah. Okay, so this one's good. Yeah, I don't know. Yeah. So what we can do, I would just delete this one. So you just gonna just go in and you just, I have no idea what time. Yeah, sometimes it's kind of weird, but yeah. Good. How you guys doing? Good.
Good. I started reading like the whole house.
I do.
No, so just the sign. And so just in part can be these 2 posts. The post is actually the main load bearing. We need it stronger.
Yeah.
It doesn't really matter. So yeah. We're gonna mesh. Is it? That's great.
I will be like on the screen.
Yeah, like that. One.
How's everyone doing on Zoom? You guys doing okay?
This over here. 003. Oh, like the rest in the air.
I hate this guy. Hate this guy. Wait, is it 1?
Oh,
-1.
what were you in that?
Cool. This.
Oh. It's like structural sources exactly like so. Yeah. I was thinking of a shot with you. Was kind of like forces on each end of the yeah.
And Professor, you want us to do different sizing for each?
Yeah, we'll talk about this. Oh.
Ready to. Oh, yeah, so you go to. And use that on which one. Yeah, instead, just.
Okay. All right, so for this meshing, right? We're taking advantage of the fact that we have an assembly here, so you can apply different meshing settings to either. Okay. One thing I want you guys to think about is, remember, mesh size is directly correlated to accuracy of the simulation, right? And so you want to have a fine mesh density or smaller elements where you think you're going to need it. Okay. Now, what do I mean by that? And so, whenever you have a structural simulation, there's always going to be areas of your model that are, more interesting than others, to kind of put it, in kind of very informal way. So for structural simulation, those are going to be locations where you have a concentration of stress. Okay. And so you want to make sure that when you run your simulation, you have a very high amount of mesh density in places where the stress is going to be concentrated. Okay. So, that's all I'm going to say at the moment for now. Maybe you can maybe kind of tell what the meshing strategy I use just by looking for mesh here. Okay. But, I want you guys to think about, after we run the simulation, after we get our results for the deformation and stress, think about, where would be a good place to add some additional elements. Okay? Should we add some additional elements to the post, or should we add it to the sign? So those are some kind of interesting questions to kind of. Okay. All right, so everyone was able to get a mesh out of this. It doesn't have to look exactly like mine. And so it's if yours uses tetrahedrons, that's fine too. Everyone got a mesh? Okay, good. Okay. So before we move on to the boundary conditions, there's actually one other thing here that I wanted to talk about. Okay. Okay. So whenever you have an assembly of parts, ANSYS needs to know how your different parts are going to interact with each other. Okay. And so what I mean by that is, you want to define, or you need to define how your different parts are connected to one another, or how they're going to contact you. And so if you go to the left-hand side of the screen, you'll see that there's a section here called connections. Okay. That section has always been there. It's just that, before today, we had never dealt with assembly. So we've never had to, look at the connections. And so if you open up the menu for contacts, right, you'll see that there are 3 contact regions. And so each of these contact regions define the interaction between one part and another inside your model. And so you can click on these contact regions and you can see, what parts do they involve. So the exact ordering of the contact regions in your ANSYS might be different than mine, just because it kind of randomizes it. Okay. Well, when I look at contact region 1, And you can look at the name, you can see the names of the parts in the bottom left-hand side of the screen as well. Okay. But this is a contact region between the sign as well as the WX2 application surface, okay? And so you can actually see both of the parts here in these windows, right? And so you can see one part highlighted is the sign, the other part is this kind of thin strip that we have on the sign. Okay. If we look at contact region 2, okay, contact region 2 is the contact between the sign and the post. Okay, so the exact region is kind of this highlighted region right here. And then once again, in these two extra windows that show up, you can see the parts that are involved in. And then finally, contact region 3 is the connection between the post and the WX2 application surface. Okay. All right. So the main thing that you have to define here for the connections is what kind of connection is there going to be. So if you look in the bottom left-hand side of the screen, so you can see I've selected contact region 2. Under the type of connection, you can see that by default, ANSYS has assigned a bonded type connection. Okay, and so what that means is that the two parts are directly connected to each other, and there should be no movement in between those parts. Okay. And so that makes sense in this case because this signpost, even though it's an assembly of different parts, you know, it's going to be secured and assembled in a way such that the sign and the post are going to be completely bonded to each other, right? So there's probably a lot of very heavy duty bolts, you know, that connect these two things. But you know, we can look just for fun. You know, we can look at some of the other options that are available for connections. So you can see that, you know, instead of bonded, you can have no separation. So no separation means that these two parts are not to be separated from each other, but they can actually slide past each other. Okay. Frictionless means that there is going to be no friction in between these two parts, right? And in fact, you know, they may separate in that case. And then rough and frictional are kind of two ways to kind of specify the same thing. And so when you have a rough or frictional surface, the two parts can slide past each other. But there's going to be some degree of friction that prevents full sliding. Right? If I recall, that the only difference between rough and frictional is that one of them will allow for separation, the other one does not. Okay. So for a lot of assemblies where your parts are kind of tightly connected to each other, you're going to go with a bonded support. Okay. But there may be situations where you're going to sometimes you're just going to delete the contact altogether. Or you're going to specify different connections depending on how those parts are meant to be. Okay. So for this, you know, for this activity, you know, we're not going to change any of these. All of our supports should be, or all of our connections should be bonded. But that's just something to kind of keep in mind for the future. Okay. In fact, in activity 4, you know, we're going to be kind of playing around with this a bit more because we have a more complex assembly for activity. Okay. Okay. Any questions on the types of connections in ANSYS? Okay. All right. One other thing that can be useful for you guys too, and I know some of you have already been doing this, is that you can actually rename some of the objects that you have here. Okay. So to rename something, you would click on that object within the project outline and then hit F2 on your keyboard. Okay. So that will allow you to rename it to something else. Right? So renaming something is not a requirement for anything, right? So you know, ANSYS, you know, will automatically kind of you know, determine names for you. But a lot of times, you know, it's kind of useful just for your own organization to, you know, rename these parts or rename the connections or rename the boundary conditions to something that makes sense to you. Okay. So it may seem kind of trivial for an activity like this where you just have 3 different parts. You know, but you're going to be doing ANSYS simulations eventually on you know, on structures with, you know, maybe a dozen parts, right? And so in those situations, it may be useful to rename your stuff so that it's easy to kind of go back and kind of see what boundary condition goes where, what connection goes to where. Okay. So for example, you know, I know that this connection here is between the sign and the WX2 application surface, right? So I can rename this to sign for WX2 connection. Okay. Similarly, for contact region 2, I can rename this to sign post connection. Okay. And then the last one here, this is post WX2. So again, something that's optional, you definitely don't need to rename these, but it could be useful when you have kind of a very complex problem. Okay. In the same way, I'm going to go ahead and rename my meshing objects as well. Okay. So I know that this body sizing object, this is the mesh sizing object for the sign. Okay. I'm going to rename this to sign sizing. Okay. Similarly, this one right here is the method for the sign. I'm going to call it sign method. This next one right here is the sizing for the post. So this is post sizing. And this one right here will be post. Okay, so just a little bit of cleanup, a little bit of things just to make your life easier when you have to go back and okay. All right, so we have our mesh. We've kind of gone over the different parts of the assembly. Next, let's apply our boundary conditions. Okay. Now, the boundary conditions in this case are a bit complicated. So let me actually return back to the project activity specifications. Okay, so we have 4 forces here that we need to apply, and of course we need to apply our fixed support. Okay, so let's look at the 4 forces. Okay, so the 2 that I want to highlight first are WZ1 and FZ1. Okay, so you can see from this figure here that both of those forces are going vertically downwards. Okay, and actually these 2 forces here are meant to represent the weights of those objects. Okay, so FV1 is the net weight of the post. Okay, and then WZ1, that's going to be the weight of the sign itself. All right. So weight forces are actually kind of interesting. So, if you look at this figure here, the way that the weights are assigned is that they look like just distributed force loads, right? And you can absolutely do that. So if you go into ANSYS, right? Go into ANSYS here, right? You can create a force load, okay? And then you can apply it on this top surface, okay? And then you can apply the numerical number for the weight of that sign. That's definitely one way to do it. But they're the more convenient way. Okay, so let me go ahead and delete this force object here. So if you're going to be applying the weights of your objects, there is kind of one object that you can put in that will automatically compute the weights for you. So if you right click on static structural, you go to insert. Okay. And you will see it near the top here that there is an option for standard Earth gravity. Okay. So standard Earth gravity will automatically apply the weight to all of the objects in your in your simulation. It's going to assume that the vertical direction is in the z direction, and so it's going to apply a vertical force in the negative z direction. Let's go ahead and add that. And so you can see here that by default, it's set the vertical direction to be minus z, but you can also change that as well. All right, so what this will do is that it'll take the density of each of your parts here and then multiply it by the volume and then apply a force, that goes vertically downwards. And this does it automatically for both the sign and the post. And so if you have a situation where the weight of the object is going to play a significant role, standard Earth gravity is a good object to add into your boundary conditions. The only requirement that you have to have if you're going to use standard Earth gravity is that you have to define the density of every material that you're using. Okay. So if you're going to use a built-in material in ANSYS, those already have the densities built in, so you don't have to add them yourself. But if you're adding your own material, just like we did in Activity 2, then you have to make sure that you add the density in if you want to use standard Earth gravity. Okay, any questions on standard Earth gravity here? All right, so that is so that takes care of 2 of our forces, and so that takes care of WZ1 and FZ1. Okay, the other 2 forces here, so we have FY1, okay, and of course we have WX2. Okay, so both of these are wind forces, so we need to apply these, ourselves. Okay, so let's start with FY1. So FY1, okay, if we read the description here, FY1 has a magnitude of 8,000 pounds. Okay? And that represents the a wind force or the wind pressure force that's being applied, to the front of the sump. Okay. So the wind force itself is not that interesting. We've already applied force loads before. But what's interesting about this force is that we're actually going to be applying it at a point. Now, I will say normally you don't want to do this. And so if you have the option to apply the force across a surface, then or even across an edge, that is almost always more preferable than assigning the force to a point. Okay. Because a lot of times when you assign a very large force to a point, what that does is that it kind of concentrates all that force onto a small point in the model, which can cause some stability issues. Okay, so I'm not showing you this just because I'm not showing you this because it's a best practices thing to do. I'm just showing you this just to show that you can apply forces at a point. Sometimes it makes sense. Sometimes it makes sense to apply forces at a point, but for this case, especially considering that this force here is meant to represent a wind that's being applied to the front of the sign. Okay. It makes more sense to apply this force kind of evenly distributed across the sign. But we've done that before, and so I want to show you how to apply force at a point. Okay. So let's insert a new force boundary condition. So let's right click on static structural A5 and then go up to force. Okay. Okay. And then to find the point, so the point is located right in the middle of the sign, but you may have trouble finding it if you're just kind of mousing over randomly across the sign. Okay. So one thing that can help is that you want to switch the selection mode to vertex. Okay. Okay. So if you click on this kind of circle part right here, right, that will make it so that your mouse is going to snap to any vertices in the model itself. So you can see that you can select all the corners here, so all the corners are points. But then if you go to the middle, right, it's a little bit hard to see, but when you mouse over the middle of the screen, there's going to be a location where a little gray dot is going to highlight. Okay. Add it in. Okay, so once your mouse is highlighting over that little gray point, go ahead and click it. I think I have it. Come on. There it is. Okay. So if you click on the point successfully, it should highlight green. Okay. And then you're going to apply that as the geometry for this force boundary condition. Okay. Now we need to apply the direction and the magnitude. So just like we normally do, we're going to change the definition of this force vector. And so instead of being applied as a vector, we're going to apply it as components. Okay. And so that's going to allow us to specify each of the X, Y, Z components individually. And then looking back on the figure here, we can see that this force is in the positive Y direction. So we're going to apply a force of positive 8,000 to the Y component of this force. Okay, so that'll put a force that kind of goes directly into the sides. So again, normally you don't want to apply a force at a point like this, but it is possible to do. All right, any questions on this? Okay. All right, so next thing we're going to do is we're going to assign the varying load force. Okay. All right, so once again, we're going to apply a force boundary condition. Or excuse me, we're going to create a pressure boundary condition. Okay, so we're going to right click on static structural A5, we're going to add a pressure. Okay. And so now this pressure is going to represent this Wx2 that's being applied on the left-hand side of the post. Okay, so first things first, let's apply the geometry to this. And so this pressure is going to be applied on this little thin strip. Okay. You want to be careful a little bit. You want to make sure that you select the entire strip here. Okay. So go ahead and hit apply once you've clicked on that strip. Okay. Now we're going to be specifying a spatially varying pressure. Okay. So according to the figure here, we can see that this pressure force is going to increase as the z direction increases. Okay. And so we just specify that as a function here in ANSYS, right? So to specify a spatially varying force into one of the boundary conditions here, you're going to use basically the same notation that you use to specify a formula in like Excel or Google Sheets. Okay. So to specify a formula, you're going to hit equals, and then you're going to type in the function. And so the function that we're going to specify is 0.1 multiplied by the z coefficient. We're going to do 0.1 multiplied by z. Okay. And so once you do that, go ahead and hit enter. And then if you did it correctly, you should see that your pressure reaches a maximum amount of 43.2 psi at the top of your model. Okay. All right, and so if you're not seeing 43.2, you may have to switch your units. And so you want to make sure that you're in the US customary unit system with inches. Okay. And so if you're not in that unit system, go ahead and switch to that, and then retype in your function. But once you kind of do those two things, then you should get the pressure values. Any questions on this? Everyone able to get that one for us? Yeah.
I'm not getting any numbers.
Okay. Let me come around in a second. Okay. So I'm gonna make another round just because I know the pressure force kind of trips people up. The last thing we need to do before we run the simulation is we need to specify a fixed support boundary condition. So go ahead and right click static structural A5. Go ahead and add a fixed support. Okay. And we're going to apply fixed support on the bottom surface of the post. Okay, and so the last thing we need to do here is we need to run our simulation. And so let me go ahead and add in the total deformation. Let's add in the equivalent stress. Okay. Just like we normally do. I know in the PDF it asks you for other stresses, but let's just go for this for now. Right, and then after that you can go ahead and solve and run your simulation. Well, there's issues with my simulation. I will come back. I will come back to this in a second. But let me go ahead and for people that are if you're having trouble applying the pressure boundary condition, just raise your hand. I'll come up. You'll have the. You need to have an equal sign.
Oh.
Equal 0.1. There you go. Yep.
We got the same.
Yeah, I need to check that. So it might. So basically, what's happening is that it's saying something with these content. It's not bonded, which is what they should. Then we have a. Yeah, I need to do it.
Is it watching for all three parts or just?
It should just be for the sign. The sign should be.
Right.
Yeah, something's going on. Let me make a round.
It's not up. Yeah, the minimum plan. It's an aluminum plan.
I kind of have.
Yeah, well, I'm wondering.
And also I play the other call.
Let's see.
Let's say what's your guys'
I have that like.
And always severely here for everything. And then I look back and she just what? I was like, okay, so that was bad.
The voice acting was forward, and that made it black mesh.
That's it.
The puzzles are hard.
There's just always like, there's a picture of a room.
Black mesh. Yeah, you go through the whole way. You go through the main, like the magic where it all started.
You did the other way around.
My body.
They are.
We made two, there's two, and everyone was after the time. Oh, good Josh. On the stage, number two.
I don't even know what that means. It's like a weird mix. Oh.
Yeah.
All the weird. It makes it even worse.
What are more efficacy? Like there's a box, this is a box.
What's your total?
But then then you get like this.
Okay, that's fine.
Well, make sure. I guess, yeah.
And then I'm pretty sure
It's gonna be at the top end. Yeah. So where the.
So if you want to-
yeah, the first one, then you'll see it back, it just has to make your lights. So it's just a point. And since like, it's a big point of view, we can't be, it's just have to guess like. Oh,
Yeah, for some reason, yeah, for me, but saying that they're fine.
You just miss the.
Yeah, I'll use it.
This is the seventh time on the section. That's the. But yeah, fix it on the bottom. You think about what rigid means?
What?
You might figure out what rigid means. If I had to guess.
Finally did.
Because the description.
What does it mean?
The deflection was found all the way at the bottom in technical inspection. It was even like in the early nineties.
I'll
So I had to go through fasteners and then fasteners I found the rigid, and then it has like, oh, it's IN 8.2. I'm like, finally, went to IN 8.2. I got 25 millimeters of deflection on.
I have the archive.
And no permanent deflection on fiber.
It's kind of dumb.
That means that like it does things like after that 100 and so it can't be more than 5.
Yeah. Like, they don't ask for our.
Yeah, that's supposed to be on.
See, but now that you're.
And also, if we're racing and it looks like the wings are vibrating, they'll just black line.
They're supposed to save it. It should be.
Like you're about it, then it's like.
Let you flip it,
Then in general, however, if you help me like that, we're wrong. It's right, our centripetal down, our centripetal one even, like, 70, 60,
I want you to help. Then they just get in the jar, it seems like. Type some question. Oh.
Because for whatever reason, yeah.
Okay, what is the issue? This guy is to me. Right. That's our lateral chair. That's pretty much like this here, using a skip that which is basically. I can just use this on, it's almost like a ball and string. Look at it around, you can see it's a consistent circle, it's not like one word, straight. So just on a full one, this is how much force we exert. And that's assuming like the center, that's not like Spreading, that's just still spreading out, like,
How many like G's?
that's stupid, because G's is that force divided by your weight. Oh.
That's actually not, that's like some fighter pilot.
That's like 5 or 6.
Yeah, you can pull that. I could do that.
I don't know. But yeah, this is there, bro. Damn, like, yes.
Okay.
I don't want to say that.
All right, so for those of you, there seemed to be an issue with the deformation being overestimated. I think I figured out the issue, so. So if you go back to WX2 application surface, it turns out the thickness of that surface was a little bit too thin. So I remember this was an issue last year where I think there was some changes underneath ANSYS that, you know, it makes it really hard for really thin surfaces to be simulated. And so what you need to do is change the thickness here. So originally we had this thickness to be 1 times 10 to the minus 3 inches. So I think what was happening was that thickness was just exceptionally thin for how big this model is. And so when we applied a force onto it, it just caused the entire surface to kind of crumple in on itself. Okay. So we need to increase that thickness. And so if you increase that thickness to 0.1 inches, 0.1 is still small enough so that it's not going to make an impact on the results at all. But it's also not going to just completely just crumple under the force, right? And so if you change that amount there, and then you go back to your results here, you'll see that the deformation, you should get around maybe 9 inches up top, and you should get a maximum equivalent stress of about 29,000 psi.
This makes more sense.
All right, so was everyone able to get this result here? Okay, good. Yeah. All right, so that's the activity, and so that's you know, now that we've kind of reached this point here, then you're good. Okay. So for the rest of class today, there's about 20 more minutes. I'll let you guys kind of work on your own for the rest of the activity itself. Okay. Okay. So if you scroll down to the activity, we've done kind of part 1 meshing here. Okay. There are some questions that you have to answer in terms of, you know, why you chose specific parts of the mesh, and so make sure you answer that in your activity report. We did problem 2, loads and constraints, and so we've applied all the boundary conditions. Okay. All right, so problem 3 is predictions, and so this is a little bit late because we've already run the simulation, so there's no need for you to predict it yourself. But the idea behind problem 3 here is that, you know, whenever you run a finite element simulation, it's always good to think about, you know, what kind of result you expect, right? Where do you expect your part to be deforming? Where do you expect the stress to be concentrated, right? Because whenever you run finite element simulations, you always kind of need to test yourself and ask yourself, you know, do these results make sense? So it's always helpful to kind of predict the results and kind of see where it goes from there. Okay, problem 4 is to analyze your results. And so for this activity here, I'm telling you that the yield strength for the post is 25,000 psi for the normal stresses, and it's 16,000 for the shear stresses. Okay, and so if we look at our results, you'll see that our results have a maximum strength of 29,000 psi, which is occurring at the bottom of this post right here. Right. So as it's currently constructed, with all the forces being applied, you know, this signpost is going to fail. It's going to fall onto the freeway and cause a big traffic jam. Okay. And so the big part of this activity is to redesign the post. Okay. And so in part 5 right here, problem 5, I want you to change an aspect of the post besides the loading. So you're not allowed to change the forces. I want you to change one geometric feature of the post itself to make sure that your post is not going to fall apart. Okay. And so some things that you can consider is that you may consider changing the thickness of the sign. You may change the diameter of the post. Okay. You may consider changing the material of the sign to make it a bit lighter. Or you can think of something else, right? And so these are kind of the first three things that come to mind, but you may think of a creative way to kind of change the design of the signpost to make it so that it's not going to just completely break us. Okay, so that's problem 5. Problem 6 is I want you to consider different loading scenarios. Okay, so in this activity here, I've given you one loading scenario where the only forces that the sign is going to be subjected to are mostly its own weight, as well as some force from the wind. Okay. But I want you to be creative and think of 2 other different loading scenarios that can happen on this signpost. Okay. And so think about these signposts, and it doesn't have to always be a freeway signpost, but think of some other forces that can be applied on the signpost as well. Okay. And so some examples of this, maybe a car hits it at the bottom, so you apply a big force on the bottom there. Or maybe you have a really fat fucking pigeon that sits on top of the signpost, right? And so that's of course going to cause some force to it. And so be creative here. So think of different loading scenarios. It doesn't have to be completely realistic. Maybe Superman comes and punches the signpost, right? So that's fine too. Okay. So I want you to simulate 2 other loading scenarios other than the default one that we have. Okay. And I want you to show me the results for that. Problem 7 is the summary, and so I want you to summarize all your results just like we did in activity 2. Okay. And then problem 8 is a different geometry. So if you notice, you go back to the Canvas page, you'll see that there is a second CAD file here that I uploaded. Okay. So that second CAD file here is for problem 8. Okay. All right, so that's the rest of the activity. So I'll be making my rounds for the next 15 minutes just to kind of answer your questions. But are there just any kind of big questions about the activity or about any parts there that I can answer? Okay, all right, so I'll be making my rounds, and so for the rest of the time, you can work on the different parts that you haven't got to yet. If you're having any questions, just raise your hand and I'll come to you. Or you can just go home because that's all that I have planned for today. So thank you guys for coming today. I hope you guys have a good weekend, and I will see you next week if I don't see you as I walk around class.
Yeah.
So. Nice.
If I want people to leave, that's it. It's like, I want to sit in one place where it's space.
Wait.
Usually when you have the solve it, they're going to use it as a tier. A lot of people have their simulations. Started oh.
I remember that.
Oh, yeah. So this is something I talked about earlier. So the thing about this.
Also, I think the increase in like this from.
Yeah, so I think, so I made this activity. Yeah, 5 years ago. So I think at that time. So. What?
Yeah. That's good.
Yeah. How you guys doing? Good.
Thank you for the good.
Oh, yeah. Oh, yeah. Sorry, it took so long.
No, you're fine.
Is that good?
Those are
Okay.
it's more than it's more than.
Okay, that's good.
I'm just right here figuring out my centripetal force of the car, assuming it goes a ball.
Yeah.
It's way too high for
What? Very hot.
that is at a weight of 140, that is 5 feet.
Yes, that would be pretty hard to sustain.
For a turn, only going 40 kilometers an hour.
Oh. Are you making like a?
It's for the car, so 220 kilograms.
Oh, okay.
Which, I just saw it out. Analysis. Okay, so it's gonna be super cycle spirit. Why you mad, bro? This is a new, originally, we wanted to go hit 45 miles per hour.
Yeah.
Ordering.
Yeah.
It's like heard of that.
How small a radius?
It's an 8-meter radius.
Still like such a big radius.
That's why, but it's a 220 but this assumption is basically ball and string. It's not like accounting for spreading it out on a wheel,
Yeah,
it's the
yeah.
all force suspend.
Yeah, that's true.
This is just the force if you swung a ball that weighed 220 kilograms.
Well, that would be a very heavy ball.
Yes, I can do a finite element analysis.
That might be interesting.
Alright, yeah.
We put in S T L.
How you doing, Sean? Good?
Yeah.
Really.
This
This
Okay.
number is accurate. We're ordering the winning car as a whole. Right?
Which means.
How's it going, Zoom people? Is doing okay?
So it's really partial. We think about all these ways of force.
I keep seeing.
Because this is just a force.
Yeah.
Either way, it's the lateral acceleration. Not about to control.
Dude.
No. No.
No. Don't say that. He's like.
Yeah, it's in my notes.
Anyways. What's up?
I mean, the numbers you.
Yeah.
I don't know what should I.
Objectives, if you have no, it's like targeting you want to, then you
Oh,
probably.
yeah.
It's already saw that. Yeah, I don't think you need like super smart.
I'm just gonna.
Yeah, so.
That's what I'm saying. I was like, I never did it.
Why did you I think that's a good.
When they put it.
That's all I was like, I'll pick downward, and I'm like, damn, he downforce like have a good number to admire.
No, that would go more into like the critical or the mental system.
Let me know if you need any more rough numbers, because I'm gonna be trying to calculate downforce this whole weekend. Yeah, it's.
It's in the data active.
Okay, I might look into it. If you want, feel free to contact me about like any forces that you want. Then I'll do my best.
It was some fun.
I'll play
Is how now is even.
I think so too. I think you could put that in.
Yeah, you're like, max out.
That's why it looks like that, but I survived.
That's how you look inside of a machine.
Is this like permanent?
No, it's not.
Like,
Oh, son.
Seven. This is one, this is almost around 1.5. That's almost 8 days.
I don't know. You guys.
I know, she's keeping her person.
I know, she looks.
She might like.
That's very.
I know, it looks like.
Before that.
Oh, Sam, you got approved.
We're going to South Dakota.
The question that was on the album looks like, oh, this has to be an event open to anyone. I'm like, actually, it's an event that's hosted by the club. We are doing direct communication, and we did offer it to the other people and mentioned that it was during the week. During a whole school week, which they would have to miss. They said no.
Yep.
That's tough. Also, Swedish seconds asked, well, if you're gonna bring back some beers, right? And I'm like, I'll see what I can do. It's like,
Or Justin.
we need them to talk to them.
Yeah, we need more events with besides ideas.
No jumping out. I'll say, like, a few of them like rock climbing and hiking.
Is that normal?
That's.
No, I said mine doesn't know.
You need to make this thing. Oh, it is thicker.
It is thicker. It's just, it's literally just.
Where was it? Oh, yours is just.
Yeah.
Oh, no, yeah, it's supposed to.
I was like, years. Is that what you have? Yeah. LBM, right? Yeah. It's not good.
You know, we all get there.
Yes.
That's what-
It's not about us, don't come here. I just, okay. I'm tired.
Yeah. Yeah, it's sure. I'm just waiting until we.
I need to finish my problem statement. Problem statement. I can sleep. No.
You don't challenge them.
The handprints would be on it.
Don't tempt me.
My fingerprints are on it more though.
Save it.
Is it? I remember I had 108 my foot.
But if you're drenching it, you're also putting my handprint, so that means I don't sit back. So if you're trying to frame it, you have to spit it out very easily.
Say my girlfriend, she don't want to move my
He brings my water as a cat. Huh? That would mean we'd have to die while committing a crime by. Cool. You know what? I think it's wrong. About that freedom of never committed a crime. He's like, wait a minute, I almost, I took that down, I'm like. He's like, I almost took it. How was it? Yeah, that's that. How much was this? That's a heavy sign. Professor, why don't we have a 15,000 pound sign?
Why don't we?
Yes.
Because we checking the mass, it says 14,465 pounds. Wait, how come it says pounds and then the M?
It's pound mass.
Okay.
Yeah.
How's that?
So it's yeah. I would forget the conversion. Yeah, it's like the mass, it's how you measure mass in English units.
It's 6,500 kilograms.
Okay. Yeah, that makes, yeah.
Way too heavy. Who hired this guy? This must be an intern.
It is a pretty simple signpost. But that's why you're redesigning it to make it better, right? The steel is very expensive. It's like one huge block of steel.
Yeah.
Yeah.
I forgot. What did you bring it? I forgot. You need to. I wanted to.
They do the homeworks,
Yeah.
but I don't,
He forgot to upload.
yeah.
Oh, okay. You can email it to me.
Okay,
Yeah.
okay, sorry.
Yeah.
Wurde einfach vergessen.
Ich weiß nicht, was das gemacht hat.